So welcome everyone, my name is Timo Grebner, I'm from the Institute of Microwave Engineering at Ulm University, and I would like to present a paper about on-sampling and bandwidth influences of distributed radar sensors on automotive SAR applications. Maybe the common way of doing mapping today is like you build a radar sensor with multiple channels, like 2000 channels. It's really complex, it's really expensive, so my idea is how can we use cheap radar sensors with just one TX element and one RX element to do high resolution mapping. And the idea is if we have multiple incoherently connected chip sequence radar sensors, so they are just synchronized in time with a BNC cable, but no LO distribution, no bistatic paths, we can do high resolution mapping. And the question is now, if we have cheap radar sensors, how much bandwidth we really need? Because if I have a radar sensor with 2 GHz of bandwidth, of course it costs also a lot of money, even if I have no channels, for example. But if we have a look into this image, we can clearly identify parked cars, we can identify a tricycle, we can identify trees, hedges, fences, and even we can separate between gravel and the street. That means we directly know where's the parking place and where's the position to drive. And the interesting part is now, if we're just about the detection and not the identification, then we can say 250 MHz is sufficient for everything we want to have, because we can even see in this image the parked cars, the trees, the hedges and the fence. So that's maybe on the bandwidth influences of SAR. Now coming to the other points, these are the coherent addition of incoherent nodes of a sensor network. That means, as I mentioned before, we are just synchronized in time and no LO distribution. That means if we have the 3 blue radar sensors and we do mapping of them, we can clearly see the antenna pattern. So we can see the car from the left, from the top and from the right. But due to the reason that we receive our signal and mix it down to the IF signal, the random TX start phase is mixed out, and therefore we can coherently sum these images, and in the end we have an image where we are able to estimate the car from left, top and right. And we can use the same approach also if you want to drive faster. In normal cases you have to drive not faster than you have a lambda over 4 spacing for SAR. If you're driving now 3 times as fast, you can see it in the blue one, you have a lot of artifacts there. So a lot of free parking spots would be occluded, and not occluded, would be reserved. So you wouldn't be able to park there. But if you're able to merge these 3 radar sensors in a way that they are interleaving to each other, that means if I have sensor 1 at position 1 or frame 1 and sensor 1 at position 2, then I can fuse sensor 2 and 3 in the middle between them, and then I still have a lambda over 4 spacing and the result looks exactly the same. So if I have 3 radar sensors, I could drive 3 times faster than it was before. And that's also the main conclusion. You could fuse incoherently connected radar sensors in a coherent manner to have high resolution mapping.